If you've coded in Python before, you've probably come across the main Python libraries. Two of the biggest examples, of course, being NumPy and SciPy. These examples are used extensively in the scientific community, and for a good reason. They provide many important functions that are used all the time in scientific research. But compared to what we're about to explore, they're nothing. With the right tools, you can take a simulation of 400 particles and turn it into a simulation of 10,000 particles, but at no extra time cost. The secret, of course, is proper utilization of computer hardware, and more specifically, the GPU, which most people have access to these days. Welcome to the third episode of the Python GPU series, the Ising model. If you guys want to support the channel and learn how to code just like me, I highly recommend checking out my Udemy course, Python STEM Essentials. Coupon code in the description, you can get the course for $10 for the next 5 days. So first thing to state is that the code on the left-hand side here is the GPU code, and the code on the right-hand side here is going to be the CPU code. So everything here we're going to run with the graphics card. We'll show it's much faster. Everything here is run with the CPU and NumPy and things like that, and it'll be considerably slower. So a good place to start is to sort of review what exactly the Ising model tells you about magnets. And so essentially it's a physical model that studies the magnetization of a material as a function of the temperature that that material is in. So for example, if you have a bar magnet and you heat it up really hot, it's going to lose its magnetization. So you need a physical theory that describes how the magnetization of something relates to the temperature. So the idea behind the Ising model is that a magnet consists of a bunch of different atoms, each with a different spin. It's either spin up or spin down. And when the spins get aligned with each other, well, then you have a net magnetic field moving through the object and you have a magnetized material. On the other hand, if the spins are all disaligned with each other, you don't have consistent magnetic field from each of the atoms pointing in the same direction, so there's a net zero magnetic field. So the spins can be aligned together, and as you heat up that material, you can provide enough energy to the system for the spins to become misaligned, and the item will lose its magnetization. So the question then becomes, okay, so what temperature does it actually lose its magnetization at? So for that, essentially, we use statistical mechanics. So let's do some little review here about statistical mechanics. And it's a very simple theory. It's actually, the Ising model, in terms of as complicated as theories get, isn't actually that difficult. But the idea here is you need some required facts. So everything here is statistical because you're dealing with large number of atoms. So a system is in thermal equilibrium with a temperature bath. That means that it's exposed to a temperature and it's come to that temperature. So you assume that the magnet is at the temperature of its surroundings. The probability of being in a state is the system, so the sort of orientations of the spins or whatever. The probability of being in that state is related to the energy of that state. So a state with higher energy, of course, you're going to have less probability of being in that state. And it turns out that the probability, well, it's proportional to e to the negative beta times e mu. So the state is mu. The higher energy, the less probability you are of being in that state. And then, of course, you sum across all the different states. The probability is 1. So you have this normalization factor z out front. Z, of course, just the sum of all possible states is known as the partition function. So that's an extremely important concept in statistical mechanics. It's not super important here because it turns out it will cancel out. So there's an important notion you have to think of what's happening here. If the system is at temperature with the surroundings, you assume that this system is at equilibrium. So what does it mean to be at equilibrium? That's actually sort of a difficult question to think about, because you could say it's at an equilibrium energy where the energy is constant, the state is constant. What does it mean to be in equilibrium? Well, the way you define equilibrium in statistical mechanics is related to this equation, and we'll sort of get into that equation below with this diagram. But basically what you say holds is that at equilibrium, the system is able to change states. The spins aren't always going to be in the same direction. For example, maybe a lot of them are pointing in the same direction, but every now and then they switch. And you could still allow that to be equilibrium. But you sort of enforce the following condition. And that's that, so nu is all possible states that the system can go to. You say that the probability of being in your state times the probability of going to this other state, and you sum those together, is equal to the probability of being in these other states and going to your state. So as often as it comes out of the state mu, it's going back into that state. And so you can think of that in terms of this diagram. If you think of mu as being the state, and the arrows are, the probability of leaving and then coming back into that state, it basically says that you're sort of going out of that state as much as you're going back into that state. So the probability P is the probability of a transition. So a spin flips, for example, that's a transition. And this is this condition over a sum is sort of hard to enforce, but you can make this statement true if you make it true for every term in the sum. So this is called detailed balance. And so that detailed balance is this equation here. And so you can rearrange this equation and you can show that this is true when the ratio of going from one state to another, this state to this state, is the ratio of the probabilities. Obviously, you can just divide that. And because the probabilities we said are equal to this, well, you just divide this by this. The partition function z cancels out. And you have e to the negative beta e nu. I'll call it v and u just to avoid confusion, minus e nu. So everything here is simple so far. You're just saying that the ratio of going from states to another is proportional to the difference in energies of these states, and exponential e to the negative beta times the difference of energies. So how does the Ising model come into this? Well, the Ising model tells us exactly what the energy of a given state is. So in the Ising model, you have a bunch of spins either pointing up or down, and the energy is related to how much of the spins are pointing in different directions. Now, it turns out that the energy, of course, for something to be pointing spin down, right, there's no preferred energy for if you take an atom on its own to be up or down, but it depends on sort of what it's surrounding it. So for something to be spin down, if everything around it is spin up, then that given state is in a state of higher energy because it's sort of opposing the direction of everything else. So you get into this complicated thing where, you can't just look at the individual things themselves, but you have to look at the neighbors. So for each point, if you want to quantify the energy of a given point, like this spin here, you have to look at, what's going on with its neighbors or its nearest neighbors. And that's where the Ising model comes into play. So you say the total energy, so ignore this outer sum over I for now. But if I pick a point I, so I is the point on the grid, so maybe I is this point here. The way to determine the energy is you sum over, so Ni would be the 4 nearest neighbors to this point. So that would be this point up, left, down, right. So Ni is the set of all these indices that are here, and you sum over all these different points. And the energy is proportional to minus J. J is a proportionality factor related to the system, so the magnet system, times sigma I times sigma J. So what it means is that if sigma I and sigma J, so remember I is the center point, and we're summing over the sigma J's, if these are opposed to each other, so one is negative and one is positive, then you get a positive contribution to the energy. Whereas if they are the same sign, if they're both pointing down or both pointing up, you get a negative contribution to the energy. So the higher contributions of the energy are where the neighbors are misaligned with the point in the center. So this sum, you then sum over all the points in the lattice, and that gives you the total energy of the lattice. So let's just remember what the idea is here. We want to take a system of spins, and we want to know how are the spins aligned and what's the energy at a given temperature of the system. So the idea behind the simulation is as follows. You start with a system of random spins, but you say it's at a given temperature, right? And then we're going to do an iterative simulation where you're adjusting spins so that they eventually reach equilibrium. So you iterate over and over and over, you somehow adjust these spins, and eventually they'll reach sort of an equilibrium detailed balance, like I said with the equation above here, of those spins. So the question is, well, if you start with random spins, how do you actually reach this condition here? Well, it turns out you can mathematically prove that if you enforce this condition at every iteration, it will eventually move into that state of detailed balance. So let's talk about, remember, we want this equation to hold, and we're going to start with random spins at a given temperature. So by the way, the temperature is specified by beta. So for different values of beta, this is going to look different. You're going to get different results in your lattice. So basically, we're going to change the system to different states nu. So we're going to go from mu to nu. So we'll perturb the system. We'll switch some of the spins. And we're going to say, well, given the probability of going to that state, do we move into that state or do we not move into that state? At each iteration, we'll change a bunch of things, and we either move towards that new state, which is v or nu here, or we stay in the old state based on the probabilities. Of course, these are the probabilities here. So This iterative algorithm works as follows. You call your initial state mu, so the state you're currently in at the beginning of that iteration. And then typically, and we'll adjust this a little in the video, you pick a random particle or point on the lattice, so, a point here, and you decide whether or not you're going to flip that, or you flip it, and then you decide whether to keep that or go back to the original. And the way you do that is as follows. So if EV is greater than EU here, so if the energy in the new state is higher, well, you're moving into a state of higher energy. So that's not preferred, but it doesn't necessarily mean we're going to reject it. You set your probabilities like this. You say P nu to U is 1. So you can set one of these, and then the other one of these is going to be the variable that you solve for. So if this is equal to 1, then the probability of going from U to nu, or U to V here, is e to the negative beta EV minus EU. That just comes from, if this is equal to 1, well, then it cancels, and you can solve for this directly equal to these energies. And that enforces the condition going sort of backwards as well. So if E mu is greater than E nu, well, then the rule above implies that U to V here is equal to 1. Because remember that we stated here the probability of going from higher energy to lower energy is equal to 1. So in this case, we are going from higher energy to lower energy, from mu to nu. So because we set this above here, this needs to be true here. So we have our probability of changing states. We start with initial spins, we adjust things, and then we accept them with the following probability. So we basically form a basic Monte Carlo simulation. So you do this, you move to a new state, and then you keep running this algorithm over and over, and then the theory tells you, or a complicated mathematical proof tells you, that eventually you reach detailed balance or an equilibrium condition. So eventually your spins will sort of get into some state where they're either aligned or misaligned, or maybe some combination in the middle. And so it turns out that there's a critical temperature in the Ising model that says at what point the spins are going to be aligned and misaligned. Okay, so let's start comparing these two codes here. And actually, I'm going to set these both equal to 1,000 for now. We'll time how long it takes to run this algorithm for a certain number of iterations. So we'll start with the 1,000 by 1,000 grid. I'm going to import all the necessary libraries in each case. And then we'll run some stuff here. So here's n equals 1,000, n equals 1,000. So the first thing we'll do is we need to generate some initial random grids of spin, right? Because we want to start with some initial state, and then we're going to let the algorithm sort of advance, and we'll move into the equilibrium state at that given temperature. So the way to do that is I actually create two random grids. I create one where 75% of the spins are pointing up to begin, and one where 75 are pointing down to begin. The reason for that, by the way, is that there's no preferred direction up or down. So if you start with 50-50 spins in the middle, it will be random whether they all move to the positive or pointing up, spin up, +1, or plus down. By starting with 75%, the one that's 75% positive, well, if that's going to move to all the spins being aligned, it will move to them all being aligned consistently in the same direction. Whereas 50-50, that initial sort of perturbation will either make it go up or down. So to do that, in each case, of course, with NumPy, you can just use np.random.random. So this is just an array of random uniform numbers between 0 and 1, and you use that to generate the lattice. So my lattice is just created as an array of zeros, and then anywhere on that array where the initial random points are greater than 0.75, the spin is equal to 1. So only 25% of random points on that 2D grid are going to be greater than 0.75 because it's a uniform random number. And then the same thing, less than 0.75 is equal to -1. I do the same basically code here with torch. Of course, this creates a n by n grid of points, and then I can create my lattices that consist of initial negative or initial positive points. And so once I do that, I can basically plot it in each case. So this is basically my grid of 1,000 different atoms on a sort of grid here in 2D. And they're going to be slightly different for NumPy and Matplotlib. Obviously, these are different random realizations. But these are sort of where they're all, most of them are starting off as positive, and then this is where most of them are going to be starting off as negative. So I have my initial grid. We're going to run the Metropolis algorithm, and all these spins are going to align in such a way that's related to the temperature of the system. If it's high temperature, they're going to be misaligned because the high temperature permits that higher energy state of the system. Whereas if the temperature is lower, well, you don't have that additional energy in the system, so the spins are going to move into a low energy state and become aligned with each other. So given this grid of spins here, I need some functions to compute some important sort of things here. And so the first thing is going to be computing the energy for a given element in the lattice. So for one of these spins, what's the energy state of that point? And then I can get a 2D grid of the energy corresponding to each point in the lattice. So this is a 2D grid of all the spins, but I can get a corresponding 2D grid of the energy of each individual element in that lattice. So this array, EI divided by J, by the way, I normalized by this J factor here in the study. Of course, it depends on the material, but we can sort of make this dimensionless here. So that's equal to this sum here. So you sum over all the nearest neighbors. You pick a point I on the grid, somewhere I, and then you sum the 4 nearest neighbors to that point, sigma I, sigma j, where sigma I is either +1 or -1, depending on the spin. To get the total energy, well, if I have that 2D grid of all the individual energies, well, then I can just sum over all the points and get the total energy. Now, it turns out you can prove that the change in energy, so for example, if I have my 2D array of points here, I can get what the change in energy of each individual point would be if I reversed its spin from up to down or down to up. So basically just multiplying it by -1 because it's either spin up or spin down. So for each of these points, I can get what the energy difference would be for that point if I change the spin. And I can get another corresponding 2D grid. So this again returns another 2D grid. And you can prove that if you change the energy of sigma I, of course it's a very easy proof, your final energy minus your initial energy is -2 times this. So that's what the change in energy for every point on the grid would be if I switch the spin. So these are basically just functions to evaluate quantities of interest. So the first function, of course, is going to be just getting the energy of each point in the grid. And you'll notice, by the way, that I give multiple lattices here, whereas I only give a single lattice here. One of the advantages with PyTorch and GPU is, if I want to basically evaluate this for many different grids, each at their own temperature, I can batch all those entries together. So rather than having a single 2D plot here, I have basically, it would be 3-dimensional, but consisting of a stack of 2D, initial configurations of spin. And then if I want to do each of those at a different temperature, well, then I run it all at the same time. But we'll get a little bit more into that later. And then the NumPy, it just takes in a single lattice. So it's easy to sort of go through this one first. By the way, if I run this thing here, this kernel, this might be the confusing part of this function here. And I actually look at this kernel. This is the NumPy version. Basically what it is it's a 2D sort of convolutional kernel. You can think of the falses as being zeros and the trues as being ones. And it basically gives you access to the nearest neighbors of a point. So for example, if I convolve an array with zeros and ones like this, it basically will sum all these points here together, the trues. So of course, one of the things you can do is you can factor sigma I outside of this sum, and you have minus sigma I times the sum of nearest neighbors here like that. And this kernel, if I convolve my grid of points, the sigma i's, with this kernel here, that gets me the sum over the nearest neighbors of sigma j. So I have this kernel here, and then that's basically what I do. When I do lattice times this convolve function, I'm basically doing, I factor sigma I outside of here. So I get negative sigma I times this sum over nearest neighbors, and the sum over nearest neighbors is equivalent to convolving this kernel here with the lattice itself. I do the same thing here in PyTorch. So I generate my kernel. It's all in NumPy right now. I convert this to a tensor, and you have to be very careful about what's going on here with the dimensionality. So you'll notice a bunch of weird things going on here. So, I can generate this kernel the same way. Of course, right now it's just going to be a NumPy array. So if I look at the kernel, it's going to have the same shape as on the right-hand side here because I've done the same code. Now, if I run this here, and then I look at the kernel, I get a very different shaped object. And it looks sort of confusing, but if I look at the shape of it, the shape is what's really important. I need to regenerate this, that's why it threw the error. So the shape of it is 1 by 1 by 3 by 3. So in this case, the kernel is 3 by 3. In this case, I have 2 additional dimensions out here. And this has to do with how we package things for the PyTorch function. So in this case, we're just using a regular convolve function, but we have to be very careful when we're using the convolutions of PyTorch, which sort of are built for neural networks. So how does the conv2D function work in PyTorch, which is the one we're importing? Well, of course, here you just, in the simple convolve case, you give a 2D lattice and a 2D kernel, and it will convolve it. Now with PyTorch, the arguments are slightly different, and you have to pay attention to what the shapes need to be. In PyTorch, the first argument, or in other words, the array which you want to take the convolution of, it needs to have a shape of batch size. So batch size can be like multiple sort of grids on top of each other. This thing called input channels, height and width. So input channels is really crucial for machine learning. In our case, each point in space we associate with a single number, which is the spin. Now, if you associate it with like spin and density and all these things, you would have multiple channels. But because each point in space in this simulation only has a like single number associated with it, that's equivalent to having like the number of channels equal to 1. But it still has to have those dimensions. It has to have batch size by input channels by height by width. So if I had multiple layers on top of each other of spins, I couldn't just give like a 2 by 1,000 by 1,000 array where 2 is the batch if I have sort of two things here. I also have to stretch it so it has this input channel. So it's just going to be a dimension with one element in it. But you need this for the PyTorch function. The second argument, the weight, has to have this shape here. So in this case, output channels, well, you know, we're taking in the tensor of spins and we're outputting what the energy of that array is. And the energy is also a single number. So the output channels is also equal to 1. Input channels is equal to 1. Height and width are going to be the same. And so this is what the shape of the actual kernel that you're convolving with needs to be. And that's why I generate these two additional dimensions. So the way I generate that is just by unsqueezing. That puts a dimension at the beginning, and then unsqueeze again. That puts another dimension at the beginning. And that's why I have these dimensions of 1 and 1 here. Because, of course, this corresponds to the output channels, the input channels, and then the height and width of the tensor. And so that also means when I give my lattices array here, it needs to have the same dimensions that's specified here. It needs to have a batch size, input channels, height, and width. Then I can basically use PyTorch's 2D convolution function. I feed in the lattices, which of course is going to be a tensor of this shape here, the kernel, which I've constructed above, and it will return an array, and the array will have the shape, batch size, out channels, height, width. So before I describe the other functions, I think it's useful to take a look at what this actually does. So for example, here I'm taking my lattice that consists of most spin down, 75% down, 75% spin up, and I unsqueeze the first dimension. So if I just do this, if I just stack the two lattices, so by the way, let's build up the shape here. If I just look at one of it, if I just look at a single lattice, it's going to be 1,000 by 1,000. Now, if I stack them together, then I have my two lattices in the same array, but I have my batch size, height, and width. But I still need that channel dimension that I specified above here. In order to do that, I unsqueeze the array, giving it the, so the dimension is 1, so it's going to insert another dimension here of length 1. And now I have my array of lattices that I can compute the energy of at the same time like this. And so I can get my lattices like this and look at the shape and it looks good. And if I compute the energy array, so this computes the energy of every given point in the lattice, and I look at the shape, so it takes a little bit and it's going to have the same shape. So that's good. So once I have my energy of every individual point in the lattice, I can get the total energy of the lattice. Well, the lattice is. If I have two lattices, so for example, all the 75% spin down, 75% spin up, I want individual energy measurements for each one of them. So for example, in this case, because I only have a single lattice, I can just sum the entire lattice array together. But in this case, I have to be a little bit careful. And actually, I can switch it like this to make a little more sense. So in this case, I'm summing over the channel dimension. Well, there's only a single dimension, it doesn't matter. The height and width dimensions. So when I return this, I'll actually get an array of length 2, corresponding to the energy of each element in the batch. And the get delta energy array, well, that's going to have the same shape as this array, and it's the same sort of equation where I just multiply by -2. So I can run all my functions here, and when I look at the shape, for example, of my get energies, well, I have two different energies for each separate lattice. On the right-hand side here, it's very simple. If I get my energy array, this is going to be a 2D array, very simple NumPy. And then this is going to be just a single number corresponding to that lattice, and this is going to be another 2D array corresponding to what the change in energy of that given point would be if I flipped its spin. So now we start to get into the Metropolis algorithm. So now that we have all these functions built up to compute the energy of each point, compute the total energy of the lattice, the delta energy if I change individual points, we can start to implement the Metropolis algorithm. So let's start with the CPU case because it's a little bit easier, and then we'll move to the GPU case. And I'm going to switch to the description of the Metropolis algorithm on the left here. We'll start with the CPU thing here. So we start with our initial array of spins. These are just going to be random. So in our case, remember we started with 75% of them up, 25% of them down. And we're going to run the Metropolis algorithm, and those spins are going to arrange themselves in such a way that, as I run this iterative algorithm, we eventually get what the true spin configuration would be at a given temperature. So we start with this spin array. Times, well, I shouldn't call it times here. I did in my older video. What it really is the number of iterations of the algorithm. So, because you don't want to have the idea that if I start this system, this iterative algorithm isn't like putting a magnet and watching the spins flip. Like that's not what this model tells you. It's an iterative algorithm. It has nothing to do with time dependence. It's only about reaching that final state of the spins. So as I iterate through my algorithm, well, I'm going to do a little trick here. Because remember I said with number 2, you pick a random particle on the lattice and you flip it. So if I do just one individual thing at a time, it's going to take a long time to run this algorithm because I'm going to be having to flip many, many, many different spins, and it takes a while. And actually, that's how I did it in my initial video 14. You'll see that this is updated. This is a much faster way of doing it. So the first thing I do is I generate these random numbers. This is either going to be random 0 or a 1, a 50% chance of being a 0 or a 1, I and j. So you might be wondering, well, what the heck is that? Well, when I compute my delta energies, what I do is I take my spin array. So my spin array is going to be that sort of 2D grid, and I only index from 0 every second element in rows and j every second element in columns. So I have my beautiful illustration of paint here. So you can imagine that if these are the individual spins in the lattice, like this, and I'll draw, I guess, a 4x4 grid here. For example, if I was equal to 0 and j was equal to 0, then I would be taking the sort of this point here, this point here, this point here, this point here, and then eventually like this point, this point, this point, this point. If I was equal to 1, I would instead be taking, well, I guess is rows. So if I was equal to 1, I would instead be taking this rows, but these would be spaced the same. And if j was equal to 1, well, then I would be taking these columns here like this. So every iteration, I'm either picking the blue here like this, I'm picking the purple like this. You can imagine it's spaced like that. I'm picking the yellows like this, or I'm picking the greens like this. So I'm considering like all these different spins sort of apart from each other like this. And so the reason why I choose them spaced apart like this is like if I picked all the points in the array and I decided to flip this and I decided to flip this based on the detailed balance condition, you run into issues here because these are actually interacting with each other in terms of energy. But if I pick them sort of split apart like this, then you never mess with the neighbors of the point when you decide to flip that given point in a given iteration. So I encourage you to think a little bit about the motivation behind that. But basically, it means that I get my grid and I'm only selecting, certain points for that given iteration. So let's actually run through these points above here. So I have my i's, I have my j's, and I have my get delta E, and I'm going to actually feed it in my initial positive lattice. So I feed in my positive lattice, I can look at the shape of DE. So DE.shape, well, it's going to be sort of half as big as the original lattice, so it should be 500 by 500. So it's going to be only those like yellow points, for example. Then I want to know, okay, so given this DE array, which is going to have like, in this case, when I flip the spin, the energy of this point increases. If I flip the spin, the energy of that point is going to decrease. So then I need to decide whether or not I'm going to keep this change or not. So am I going to keep the flip of, for example, this yellow point, or am I not going to keep the flip of that yellow point? Well, for that, I need to look back at this equation here, that the probability of going to this new state, well, if the new energy is positive, well, then the probability of the flip is going to be e to the negative beta times delta E. So I need to evaluate delta E for each point in this array, which is what I've done, and I need to accept it. I need to only accept that with this probability. So the way to do that is I generate a bunch of uniform random numbers. So all of them are between 0 and 1. And if that value is less than this exponential, which is sort of this value here, then the change is true. So that means you keep the spin flip and you stay in that state, right? So this is for the case of where DE is greater than or equal to 0. For cases where DE is less than or equal to 0, well, then I say you necessarily go to that new state. So that's why I add this here. This is all Boolean logic. So change will be an array consisting of either yes, keep the change, or no, don't keep the change. So by the way, if I give this array here and I look at this DE and I sort of evaluate this, and let's do it for a temperature of 0.5, for example, and I look at the form of change. So it says, okay, well, this one was positive, we're false, we're not going to keep it. This one was positive, false, we're not going to keep it. This one was positive, false, we're not going to keep it. So if I increase the temperature, remember there's more energy in the system, it allows these spins to be in whatever configuration they want. So I decrease beta to 0.1. Remember, beta and temperature are inversely related. Well, then some of these points that have positive, for example, well, they just end up to be true. So this one had a positive change in energy when I flip the spin, and it's equal to true. Remember, we're dealing with the yellow points on this grid here. You can think of it that way. And some of the positive points, well, you're not going to flip. But whenever the change in energy is negative, like -8 here, you're necessarily going to flip that spin based on this equation here. So this tells me whether or not to flip the spins. It's either true or false. And then I sort of go through. So I index my array at all those sort of yellow points you could think of on the grid here. And I, based whether they're true or false, I multiply this spin array by -1. So I flip the spin. So I've modified my system. Then I get the energy for that grid and the average spin from that grid using basically the get energy function. For this, I just sum all the spins together, right? And I divide by the number of atoms that there are, and that gives me the average spin. So in the CPU code, I only had a single value of beta J here. You're just doing this for a single temperature. The reason why I started with this is now we can move to the GPU code, which is a little bit more optimized. In this case, we have a batch of spin tensors. So for example, I can give 6 random initializations of spin and then a different temperature corresponding to each one of those. And the advantage of using this convolution 2D function here above, where was it? It was right here. And so the advantage of using this conv2D function that I have here is that I can take in a batch size of multiple tensors. And I can do sort of multiple things at the same time. That's sort of the moral of the story, the lesson of using PyTorch is that you're trying to do many things for a batch at the same time. You're moving away from for loops and you're sort of thinking in terms of this batch operations on data. So I've taken this batch of spin tensors. The way that this algorithm will work is I'm going to have a different value of temperature, a different value of beta J for each spin tensor. So this allows me a lot of opportunities here. So maybe I have 75% positive, 75% negative spins. Well, then I can give the same value of beta J for each one of those if I want to compare them. But another option here is that I have a batch of many grids that are all 75% positive to begin with. And I have a different value of beta J for each one of those. And then I can see, well, for all these different temperatures, how does it approach equilibrium for each temperature case and get sort of the average energy, for example, or the average spin as a function of temperature. So the code is mostly the same. The main thing to note now is the beta J, I reshape it. It has 3 extra axes here, and you might wonder why I'm doing that. Well, remember where beta J showed up here in the exponential. It was a number. And you have to think about what the shape of my DE is. Remember that DE is going to have the same shape as the spin tensor batch, which is going to have batch size, 1, height, width. So my beta J's, they also need to have, well, it's going to have batch size. This is what the -1 does. It automatically inserts the correct dimension. So beta J is a tensor that has 2 elements in it. This thing is going to have 2 elements by 1 by 1 by 1. So it allows me to sort of operate this beta J tensor, multiply it by a tensor that has this same shape here. So that's why I include it, and that's why I can do this operation here. So basically, while this one will give you the spin as a function of iteration number for the single spin array that you're considering, this one gives you the average spin as a function of iteration number. So for example, if there's 2,000 iterations, 2,000 numbers, but it also gives you it for each spin tensor in the batch. So for example, if I run this code here and I look at the shape of my spins.shape, because there's 2 things in the batch, there's the 75% positive and 75% negative, then it's going to have this for each one of those. Whereas here, you'll note that this took quite a bit longer to run. This took about 24.4 seconds as opposed to 3. The other thing you should notice is that here there was only a single lattice, and here I was running both lattices at the same time. So this one here is easily greater than 10 times faster, about like 15 times faster using the GPU than the CPU for this particular algorithm. And I promise you that that will only increase with the number of points that you use on your grid. So in this case, we use a 1000 by 1000 grid. As that number goes up, the GPU will only be more and more efficient. But anyways, the thing to notice here is that the spins.shape here is only corresponding to a single lattice. So you'll notice that with the GPU code, we're trying to do many things at the same time in our code. So now we can plot the spins as a function of iteration number, and we want to show that they're the same for the CPU and GPU code. So in this case, I'm looking at the spins corresponding to the 75% up lattice, and I can do that here as well. And sure enough, the sort of curves look exactly the same. I don't know why this says beta j is 0.7. I'm just going to remove the subtitle here. This is for beta j is equal to 0.5 here. So here I have a tensor with two 0.5s in it. If you're confused about that before, it's just 0.5, 0.5. So of course this had 75% of them pointing upwards, and the temperature was not hot enough to have them be in a random configuration. So as the iterations went on, the spins became aligned with each other. And so that means that at the equilibrium, well, your spins are going to be, they're not totally aligned. The average spin wasn't equal to 1, but most of them were aligned with each other. So now what I'm interested in is, okay, well, here I did it for two different lattices, 75% pointing up, 75% pointing down, but they had the same beta j value. Now I want to do it so that I give it a single lattice. So I give it, for example, a 2D tensor where I have 75% pointing up, for example. And I want to evaluate what this curve looks like for a bunch of different beta j values, a bunch of different temperatures, essentially. So the way to do that is I take my initial lattice and I repeat it a number of times. And so if I take an initial lattice, for example, if I just look at this for my lattice positive, I believe it's called, and I look at the shape of this, it converts it in such a way that I now have two copies of that same lattice for each different beta j value. Now, if instead I had like 10 different temperatures I wanted to look at, you're now creating a tensor that's a much larger size. But again, it has the dimensionality you need to be run in that conv2D function. So now I have this much bigger batch size of lattices, and I can compute the average spin, average energy, and the standard deviation of energies, maybe how it varies at equilibrium, as a function of these different temperature values here. And it will return it. So for example, I can run this code. So now I'm looking at... this is a little bit confusing here, but remember that temperature is inversely related to beta j. So I do 1 divided by this linspace array here. So this is temperatures from 1 to 3. We're going to look at 20 different points here. And what we'll do is we'll find the dependence of the average spin versus the temperature for both 75% pointing up. So that's sort of this first array here. Or that's pointing down, and 75% pointing up. That's the second array here. So we're going to evaluate it for 20 different temperatures in each case. So you'll note, by the way, that this took 24 seconds to run. So if I wanted to evaluate this for 20 different temperatures, you could think of how long that would take. In this case, this runs in 43.5 seconds. So we've evaluated it for all these different temperatures, and we can look at the average spin as a function of temperature, and we get this beautiful curve here. So, for example, when 75% of the spins started negative, well, at lower temperatures, they all align with each other because they have to be in that state of favorable energy when there's no energy added by temperature. But as you start increasing the temperature of the system, then you have all this excess energy moving into the system, so the spins don't necessarily have to be aligned with each other anymore. You have sort of heat energy allowing things to go in energetically non-favorable configurations. And you have this concept of this critical temperature where you move from the spins being completely aligned with each other to being completely misaligned with each other. So that's like a phase change. In fact, it is a phase change. It's very analogous to what happens when water freezes or melts or turns from liquid to gas. You have a phase change here of a magnet being magnetized to being completely unmagnetized, which is what you see here. I'm going to move into the 3D Ising model here now. And remember that as you move from 2D to 3D, you're going to have a much bigger grid of values. And so rather than 1000 by 1000, we'll do 150 by 150 by 150 for 3D. Of course, you could increase the size of this, but that depends on the sort of memory in your GPU, things like that, etc. But basically, all the code here is the exact same as the above, only we're in 3 dimensions. So now I create my initial grid as 3D like before. I have to be a little careful with the kernel. Now it's a 3D kernel where you have up, down, front, and back. So then I have to add the batch and the channel dimension to the kernel, and I can use the conf3d function here to compute this. So it's basically exactly analogous to above. I can stack lattices together, and of course in this case, lattices.shape, we're going to have something that is much different. So now I have a 3D grid. This is my channel dimension because each point in that 3D grid has a single number, and I have 2 different lattices here. So now that I have my Metropolis algorithm defined, I can have the same sort of function as before, only in this case I'm in 3 dimensions, and it will take my single lattice, it will duplicate it, and then evaluate sort of this Metropolis algorithm for each thing at a different temperature. And we'll say, what does the average spin converge to for different temperatures? And that's what this function does here. So now I'm going to look at a bunch of temperatures between 3 and 5.5. Again, beta j is the inverse to temperature. I'll put this on my device, my GPU, and then I will get the average spin, mean energy, and standard deviation of the energy of this 3D grid now for each different temperature. So we've solved this in 1 minute and 20 seconds. And by the way, I want to talk about how impressive this is, because I remember doing the Ising model in my undergrad, and I was doing it just in 2D. And I was a new programmer, and I was trying to run the simulation. And I remember it taking myself and other people in my class, like, leaving your laptop on and letting it run for a day, 12 hours, to get all the measurements you need. And then when it finished, this plot that you got here, we were only doing it in 2D. And it didn't even look this good because we weren't able to simulate that many points. It was a very ugly looking plot. And that was 2D. And in the code in this video with your GPU, we're upping to another dimension here. And we're actually able to solve it in 1 minute and 20 seconds. And by the way, so the 2D Ising model, it turns out you can analytically solve for that critical temperature, or the temperature where sort of this switches here. In 3D, because of, I don't know why, I'm not that smart to understand, but you can't solve it analytically in 3D. So you have to simulate it numerically like we did here. And the accepted value for the critical temperature, according to this paper, is beta j is 0.221654626. So they do a bunch of simulations with different lattices, and you can get a sort of accepted numerical answer for what the temperature is where it switches. So here I actually put a vertical line corresponding to that temperature here, and you can see that we get this beautiful looking plot. And look, like you can see the time it takes for this transition here. So as you move from sort of 3 to 5.5 units of temperature, it starts to decrease here. And then, of course, this point where the accepted critical temperature is, well, it's sort of somewhere in the middle of this decrease here. If you made it to the end of this video, congratulations. I'm impressed that you were able to stand me for 50 minutes rambling on about this stuff. I hope that the code was useful for your own projects in the future. Like in previous videos, and people have done this, and I really appreciate this as well. If you have advice to speed up the code or make it faster, please be sure to let me know. Join the GitHub or just leave a comment on the video. And if you give something that significantly speeds it up, I'll be sure to give you credit when I update the code. Anyways, thanks for watching. Please like and subscribe. Join the Discord server as well. There's a link in the description, and I'll see you next time.